Okay, so hi everyone. Welcome to an introduction to induction. I'll just be taking the what induction is and a few problems on it. So first of all, induction has two types. There is weak induction and there is strong induction. So we'll start with weak induction. Basically, weak induction has two things, two conditions. First, you want to prove that it holds for if you're given a condition, you want to prove that it holds for n equals 1. And you also want to prove that if it holds for k, then this would imply it holds for k plus 1. And this would basically prove the statement. Okay. Do you guys get this?
Yeah, we get.
Uh, yeah, sure. N equals 0 also is fine. I mean, basically, you want to have a kind of minimum value for which it works. Like, it could even be n equals 5 for some problem. It like doesn't matter. Yeah, base case. Negative numbers, no, you can't like do this for negative numbers because like there is no minimum value. But for example, if you prove it for n equals 0 and then you prove for n implies n plus 1 and n implies n minus 1, for example, then that would also work. Okay, so I'll just give an example problem. Prove that you guys can try this. So anyone want to give the solution to this?
Uh, I mean, it's kind of obvious that it holds for n equal to 1, then it's like plug in and check. And like if we assume that it holds for k, then like, just add k plus 1 squared, and then like it will also work.
Yeah. So basically what you want to do is you want to follow these steps. So it holds for n equals 1. You can like just see that 1 squared is equal to. And you for now you assume like you take you know that this is true and you want to prove that this is true. But now notice that this the LHS is basically equal to uh,
Won't it be 2k plus 2?
no 2k plus 3, like this is uh, 2 times k plus 1 plus 1.
Oh, okay.
So yeah, you have this plus k plus 1 squared which is this is just the algebra part. It's like so. Yeah, did everyone get this?
Yes.
Yep, we get.
Okay, nice. So now I'll give you a slightly harder problem. Try proving this. Uh, you guys can try this problem. If you have any ideas or anything, you can message me privately.
Can you explain the question?
Uh, the question is basically if you have a natural number n, then you want to prove that there is an n-digit number that is divisible by 5 to the n. So like for example, if you take n equals 1, then you have 5 is divisible by 5 to the 1. For n equals 2, oh wait, sorry, my bad. Yeah, this is an extra condition. All of the digits have to be odd. So yeah, for n equals 1, you have 5. Then for n equals 2, you have 75, which is a multiple of 5 squared. For n equals 3, you have 375, and so on. Yeah, no, I added the condition later. My bad. All the digits have to be odd. Okay, does anyone have the solution or an idea? Okay, sure. I'll wait.
I'm getting a feeling that like you can multiply by either 5 or 25, and like one of them will hold true. Maybe even alternately. I don't know. Like, if we multiply 375 by 5, we'll get 1875, which is like not. But if we multiply that by 5, we get 9375, which does hold.
Okay, yeah. So you're multiplying by something, right? So what you got for n equals 4 is 9375. So are you noticing anything about this?
Oh, yeah, we are just adding digits.
Yeah, exactly. So yeah, the idea of this
I have
problem,
a solution. Can you? I don't think that that would be appropriate, but can I tell you?
yeah, sure, sure.
Okay, if we define a k to be a k digit number. Okay,
Yeah,
for one there exists five. So let for k it is true, and ak 5k divides ak. 5 to the power k divides ak.
yeah,
Uh, so now for k plus now 5k divides ak, and if we multiply by 5 to each term, 5k plus 1 will divide 5k into 5, right?
yeah.
And 5k into 5 can be a k digit number or a k plus 1 digit number. So to ensure this, we can multiply 2, so that always be a k plus 1 digit number. So 5k
Hang
plus
on, hang on. If you're multiplying 2, it won't work, right? Because if you're multiplying by 2, then the last digit would be 0.
yeah, but
Yeah,
5k plus 1 will divide it.
yeah, but like all the digits have to be odd.
Oh, okay. So can we multiply by 3?
Okay, and I am not sure if that works exactly, but like you want to induct on this problem, right? So naturally you would induct on the number of digits.
Okay, okay,
So now the point is that you have a number for you have some number from for n, right? And you want to find a number for n plus 1. So now what you want to do is you want to keep this number a substring of the next number. Like you know that like what you said ak, 5 to the k divides ak. Okay, hang on. Yeah. So 5 to the k divides ak, and you want to find a number for ak plus 1. So now you check, like you add a 1 to the beginning of this number. For example, like you have 9375, you will take consider the numbers 19375, 39375, 59375, 79375, and 99375. Okay. Now, do you guys see why this so we want to prove that one of these is a multiple of 5 to the k plus 1. So do you guys see why this will hold?
Yeah, I think even two of them might be multiples, but no. Okay, wait, only one will be, but
Yeah, exactly one will be. So do you guys see why this is going to hold?
Only they all leaves different and
yeah, if we divide, they are all clearly divisible by 5 to the k. If we divide by 5 to the k, then we'll just get like the entire residue set mod 5. So one of them has to be 0.
Yeah, exactly. So yeah, when you're adding this digit, you're basically doing AK plus like 1 of 1, 3, 5, 7, 9 into 10 to the K. So this basically means that this term will be divisible by 5 to the K. And now you have that this term, like all of these 5 different terms will have distinct remainders mod 5 to the K plus 1, right? Because all of these are distinct mod 5s. So no matter what remainder this has, like this has the possibilities of being 0, 5 to the k, 2 times 5 to the k. So like this has all 5 distinct remainders. Like this could be any of the remainders, but no matter what it is, one of these will satisfy uh, the number we require. Does anyone understand this?
I don't get it. Can you repeat again?
Okay, so see, basically for 75, what we have is like you have 5 squared divides 75, right? Now, if you want to add, like you want to add a digit in the beginning of this. So assume you add a 1 in the beginning. So that's basically like doing 100, right? You're like adding 100. So the point is like you can add 100 or 300 or like whatever till 900. And sorry, yeah, this will basically be like you're either adding 1 into 10 squared or 3 into 10 squared and so on. So like what you can do is 75 is equal to 3 into 5 squared. So like 75 mod 125 is going to be like, it's going to be 75 mod 125, like 5 or 3. So now when you get these numbers, like you know that this is congruent to 0 mod 5 squared. And this is like basically 4 into 5 squared, 8 into 5 squared, 12 into 5 squared. Do you get this? Like we can write these numbers as this. And now notice that all these numbers are distinct remainders mod 5. Like this is 4, this is 3, this is 2, this is 1, and this is 0. Do you get this part? Uh, who were who was asking that out?
Yeah, I get it.
Yeah, so you have all of these, and now you have 75, which is 3 into 5 squared, right? So if you added a number which is like 2 into 5 squared, so like you basically add uh, this number, like 12 into 5 squared, what you will get is, hang on, wait. Yeah, what you'll get is like 5 into 5 squared, which is congruent to 0 mod 5 cubed. These numbers will be like different, but you get the idea.
Okay, okay.
Yeah. Okay, does everyone get this?
How will we write that formally?
Yeah, formally you can write it like this. You have that 5 to the k divides ak, and you want to find ak plus 1. So like ak plus 1 is equal to ak plus 10 to the k into 1 of 13579. And notice that these are all distinct mod 5 to the k, right? So you note that AK has 5 possible remainders mod 5 to the k plus 1. And you also notice that this has 5 distinct possible remainders. And like one of them will definitely add up. 5 to then does not have end digits. And like 5 to then, like any power of 5 has 2 as the second last digit. So like it won't satisfy. Okay, does everyone get this part? Like how we finish the problem?
Yes.
Why we don't take 2, 4, 6, 8?
No, it's like given that all the digits are odd, so we can't add 2, 4, 6, 8.
Oh, okay.
Nikhil, you're saying that 5 to the n has n digits, but like this doesn't work because like 5 squared is 25 and like 2 is like even, so you can't use that.
Why should it always be AK plus 1 equal to AK plus 10k? Why this AK term appears?
Oh, we don't have to use it, but like it's convenient, right? Because we know for sure that this AK is satisfying the original condition that all digits are odd, and we also know that 5 to the k divides it. So like we're just taking this AK and using it in our inductive step.
Oh, okay.
Okay, so I'll move on to strong induction. So strong induction is basically like quite similar to weak induction. The conditions are the base case holds for n equals 1, and we want to prove that so notice the difference here. You know that it is true for all integers up to k, and you want to prove for k plus 1. So yeah, it's slightly different. Everyone got this right? Strong induction, like the difference at least.
That's why it's called strong.
Yeah, you need a stronger condition. Okay, so I'll assume everyone has understood. I'll give you a problem on strong induction. You have a town.
Can you please have a solved example at the beginning, please?
Sure, I can explain this example like by solving. So you have a town with n cities, and you want to each city has a one-way path, each pair of cities. The this one-way path could be in any direction. So you want to show that there exists a path going through all cities. A path is like basically between two cities there is a road. Like if you have A, B, C, so like you can go from A to B, you can go from B to C, and you can go from A to C. This is an example of the town. Now, what do you mean not necessarily that they are adjacent? No, it's not n is just like it's not a connected graph or something. The paths are one way. Like you can't go from B to A. So
Oh, acha, it's one way. Okay, okay.
yeah. Nikhil, what do you mean by they are adjacent? Like okay, okay, sure. So yeah, I'll give you a few minutes to try this.
One way path means
One-way path means you can only go from, like in this example, you can only go from A to B. You can't go from B back to A. Yeah, okay. Does anyone have any ideas? Nikhil, if you don't know how to write a proof, you can just explain what your idea is. Path going through all cities means like, for in the example that I've written here, you can see that there is a path going from A to B and then to C, right? Like you can go from A to B and C. For example, I'll take a larger city, like a larger example. You have A, B, C, D, and you have these kind of one-way paths. So now here you can see that there is a path going from D to C to A to B. So like it's a path going through all cities. Yeah, it is necessary that every pair has a path. Every pair of towns has a path. Nikhil, you are saying that if there is a path for n cities, then there will be a path for n plus one cities. But like, what is your argument? Can you like explain exactly?
Can I give my solution?
Yeah, sure.
So you add a point, and then uh, there must be an edge going through the direction, going through the direction to the new point or one of the old point. So if there is a point going through the facing to the new point, then for the end points you have a path going through all cities. So from the end point you connect it to the new point. So the new point will become the new end point, and the proof is complete if that is the direction. And if there's no uh, if there's no edge with that direction to the new point, then then the new point comes in the between of the path.
Uh, you're saying that like okay, assume in this example you have a point E. So you're saying that assume there is a path going from C to E, for example, then E will be the endpoint.
Yeah, E will be the end point.
But like, what if C is like not the ending point of any of the paths of this n city then?
There must be an end point for A, B, C, D, E. Sorry, A, B, C, D.
Yeah, so assume the endpoint is B
Okay,
and
so
the path
from
is going from E to B. So what will you do?
uh,
But yeah, you're thinking in the right direction. The induction is like on the number of cities, and you have to consider which path is going inside or outside.
E would be the starting point in that case.
B cannot be the starting point, right? There is nothing, no path going outwards from B.
From E.
Oh, E would be the starting point. Yeah, but then again, like if you're going from E to B, for example, so like, I mean, how would you construct the path then? Like here, the path for n plus one cities is D to C to A to B, right? Now, like where would you put E in this scenario? You can't put it at the end because like B has to be the endpoint. And assume, let's say you put it like you can't even put it in the beginning, for example, because there might be a path like this, like D goes to E. So like you can't exactly put E at the beginning or the end, right?
I mean, okay, if all of the points, all of the paths are pointing towards E, then we are done because just follow the normal path. And if not, then at least one of them exists such that like it points from E to some to one of the old points. So we can just say without loss of generality, like E to B it points. Then and like okay, wait, no, there is some.
Okay, by the way, guys, just remember this is an example of strong induction. So you guys are looking at this in the weak induction way. So maybe try think of something that involves strong induction. Okay, so I'll give you the idea.
Okay, wait. I think I have like for example, the path points from A to B, so we can split the graph into like two other graphs, one with 2 points and one with 3 points. And in the 2.1, there will be this path, and in the 3.1, there will also be this path. And like there should be a way to go from to the 2.1 to 3.1 or vice versa.
Okay, you have the correct idea. So
Just the end point and starting point thing I have to.
exactly the endpoint and starting point, right? So what you want to do is you want to find something that's like that has an endpoint and a starting point. Like you want to know that the endpoint is in the direction you want it to be. So you have k cities and you have like you're adding one city extra, right? So consider the all the paths going outwards from this k plus one city, right? And then consider all the paths going into this city. So now you can split these cities into two groups, right? Group A and group B, such that every city from B has a path going to k plus one, and every city from in A has a path coming from k plus one. Do you guys see the idea now?
Oh yeah, then in B there is this thing, this path, and from B, like from the endpoint we can go to K plus one. From K plus one we can go to A, and in A we can just tour all the cities.
Exactly. So now here you're using strong induction, right? Because A and B can be of any size. So you're using the fact that
A
it
and B
holds
are
for
less than
all
K,
of them.
so yeah.
Yeah. You're using the fact that it's holding for every single number from 1 to k. So it will hold for no matter what A and B is. Do you guys get the idea? Okay, so basically what we're doing is you have these cities, right? Uh, A, B, C, D, E, for example. Now you just take the city E outside. And now you have this group of cities such that E has a path going towards them. And you take this other group of cities such that they have a path going towards E. So like you know that every city has a path either going towards you or coming from you. So you can split these cities into two separate groups. Okay. Now we have assumed that it is true for all integers up to k, like no matter what k is, which like for example this is like n equals 6. So we know that it will hold for all groups of 1, 2, 3, 4, 5 cities, right? Do you get this part? Okay, so now that you have this, notice that both of these groups, first of all, they don't have a single city in common, right? And both of these groups have to be less than 6 because you're taking one city out. So you know that there is a path going through all cities in this group, and you also know that there's a path going through all cities in this group. Now, no matter where this path ends, like call this group A and call this group B. So like no matter where this path ends in group A, there will always be a road going to E. And no matter where the path in group B starts, there will be a road going from B to that city. So like you have a path going through every city in group A, then through E, and then through every city in group B. So basically it's going through every single city. Group A is the set of all cities that have a path going to E, and group B is the set of cities that have a path coming from E. Does anyone have any questions?
What if group A is empty?
But that doesn't matter, right? Because then group B would still be like n minus 1, which would fall into this set that we have. So we'll just choose E as the starting point and we'll go to some city in group B, like whichever is the starting point of that path.
Okay.
So yeah, basically no matter the size of group A and group B, we can always find such a path. Okay, I hope everyone understood this. I'll, a path is like going through, like you can travel through every single city. What do you mean if the path is going from E to A? Like, no, we're taking group A as the set of cities such that they're going to E. Like, you cannot have a path going from E to anything in group A. Yeah, A is defined like that. Okay, wait, let me like explain with an example to make it clearer. So you have this set of 6 cities. Let's call them 1, 2, 3, 4, 5, and 6. And you have uh, these paths, for example. Okay. Now you know that the statement, the problem statement is true for n equals 1, 2, 3, 4, 5. Okay. Now you take this city, the sixth city, and you make a graph like this. So you can see that the sixth city has paths going to 1, uh, 3, and 4. And it has paths coming from 5 and 2. Okay, do you get this part? Yeah, okay. So now the edges between 1, 3, 4. Now you call this as group A, and you call this as group B, right? Now you know that the statement is true for 1, 2, 3, and 4 and 5. So like notice that the sizes of both these groups are less than 5, or like less than equal to 5. So you know for sure that there is a path which is going through every single city in group B, and also a path that is going through every single city in group A. Right. For example, now in this case, the path is going from 2 to 5. And in the 1, 3, 4 thing, there is a path going from 1 to 3 to 4. So yeah, oh yeah, they're all interconnected. I mean, you're not deleting the edges, right? You're just forming this kind of separate graph, which is like a subset of the edges. Okay, cool. So yeah, you basically now your path is decided, right? You go from 2 to 5, then to 6, and then to 1, 3, 4. So you're using the fact that it's true for everything less than n to get n. Oh, and yeah, uh, if the if for example group A is empty and group B has 5 cities, it doesn't matter, right? Because it's proved for n equals 5. So like if you choose 6 as the starting point, you will reach some city in group B, and like you can reach any city in group B you want, and from that city there will be a starting path. Okay, cool. Okay, I hope everyone has understood. Uh, can I move on to the next problem? Okay, cool. I'll paste the next problem. Give me a second. Okay, so you guys know Fibonacci numbers, right? Okay, so I'll just define them for like clarity. F0 is equal to 0, F1 equals 1, and Fn equals. Okay, so now you want to prove that f of n plus 2 minus 1 is equal to f of 0 plus f of 1 plus and so on, plus f of n. So any ideas you can message me privately.
F of n plus 2 minus f of n is equal to f of n plus 1, then you will get same condition.
Yeah, perfect. So yeah, you just take f of n plus 1 minus 1. Like you transpose f of n to the left hand and you get this condition. So this is the inductive step, and it's obviously true for the base case. Like you have f of 0 is equal to f of 2 minus 1. So yeah, everyone understood this, right? Yeah, this is trivial. Okay. Uh, what do you mean? Why did I do? Like, are you asking for the motivation behind this step? Okay, so yeah, basically the motivation is you want to induct, right? So you're assuming that it is true till n. You're assuming that this is true. Uh, you're assuming this is true, and you want to prove. So what you will do is you basically notice that this is equal to, right? And we have already that this is equal to f of n plus 2 minus 1 plus of n plus 1. And so you get uh, what we wanted to prove. So basically the transposition of f of n is basically the reverse of whatever this is. Yeah, this is a weak induction. Strong induction is not that common. I mean, weak induction is only like, way more common than strong induction. Okay, so no questions, right? Or does anyone have any doubts? Okay, cool. Okay, so yeah, try this problem. You have a tromino of this shape. It covers 3 squares, and you have a grid of square grid with side uh, 5 into 2 to the n. So what is the maximum number of cells you can cover using only trominoes of this shape? And there is obviously no overlapping. And you can like rotate or reflect this tromino however you want. Okay, you have a tromino of this shape, which covers 3 cells on a grid, and you have a square grid of side length 5 into 2 then. So for example, for n equals 0, you have like basically a 5 by 5 grid. So you want to find out the maximum number of cells you can cover using only these trominoes. You can rotate and reflect. A maximum number of squares you can cover. Like for example, not for this question, but like if it was, let's say 2, so you can cover like at most 3 cells, right? By this strong. You can't cover the fourth cell ever. The 5 is like you can choose any. Like for example, n could be like if n is 0, then it would basically be a 5 by 5 grid. If n is 1, it would be a 10 by 10 grid and so on. So you want to like find the maximum number of cells covered for any n. Okay, anyone has any ideas? First of all, for the n equals 0 case, the base case, can anyone find like what is the best tiling for this? Make 2 by 3 blocks. Yeah, yeah. So yeah, that's like a good idea. How would you do that?
with two trominos.
No, no, I mean like how would you cover the 5 by 5 grid with 2 by 3 blocks? So like what is the max you're getting?
I mean, if we do that for n equal to 0, I think four four cells are.
4 cells? Like 4 cells are remaining.
Yeah, 4 cells are remaining.
Okay, can you do better?
Yes, we can reduce it to only one cell left.
Wait, how do we reduce it to one?
There are like multiple constructions.
Okay, let me think.
So okay, first of all, like that's not the important part. But like 5 by 5 is like just finding a construction. So like you can, like you said, you can make these 2 by 3 grids, right? Using 2 trominos. So what you can do is you can fill in this, and you can fill in this. Okay, so notice that you have covered 24 of the 25 cells and only the corner cells left. So like for n equals 0, the answer is basically only one cell is uncovered. Now, do you think you can extend this?
Yeah, if we have like after that we will have a 10 by 10, right? So we can split it into four 5 by 5, and we can make it such that the ones which we have not covered are towards the center, and out of the four we can cover three of them with an extra domino, so one will be remaining. So I think that
Exactly.
is.
Yes. Does everyone get his idea?
Can you repeat that?
Yeah, okay. So you have the like you have that for a 5 by 5 grid, you have all of these cells covered and only the corner cell is left, right? So now take the 10 by 10 grid, you split it into four 5 by 5 grids like this. So all of these are individual 5 by 5 grids. And now you can like basically tile this, but like you can reflect it so that only this cell will be uncovered and all of these will be covered. Then similarly for this 5 by 5 grid, you can leave only this uncovered and all of these covered. And same for this one, you can leave this uncovered and the rest covered. And then for this top one, you can leave this uncovered and the rest, all of them covered. And then you can put a tromino over here and you have a 10 by 10 grid with the corner cell uncovered. Do you guys get this?
Yeah, we get.
Okay, nice.
But
And
but how did we get this type of motivation?
The motivation is basically like you want to induct, right? Like you have a construction for 5 by 5, and you it's kind of like intuitive that you can cover all except one, because basically all of these numbers are going to be 1 mod 3. So you want to find the tiling that will work for like no matter how big the grid is. So what you would want to do is you want to take the styling that you already have, and you want to like kind of make a like you want to use it in a like in the 10 by 10 you know that you can split this into 5 by 5 grids, and you have control over this cell that is uncovered. Like it can be in any corner. So you can just align the corners such that they will form a domino, and you can repeat this pattern. And again, for the 10 by 10, you can like, if you consider like the n equals 2 case, so like 5 into 2 squared, it would be a 20 by 20 grid. And again, you can split this into 4 10 by 10 grids. And you have a 10 by 10 coloring, which leaves only the corner uncovered. So you can repeat this configuration. Do you guys get this?
We should also like prove that one is the best we can do, because like it is the number of cells is 1 mod 3.
Yeah, yeah, that is like trivial to prove. I mean, the total number of cells on the board are 5 into 2n squared, and this is congruent to 1 mod 3. And each tile covers exactly 3 cells, so you cannot cover that last cell. Okay, I hope everyone has understood this. Any doubts? One tile is not colored because, like for example, the 5 by 5 grid has 25 cells total, and with each tile you can cover exactly 3 cells. So like 25 by 3 is not an integer, so you can't cover that last cell. Like you can have a maximum of 8 tiles on the board, and that means you can cover at most 24 cells. Okay. So I'll move on to the next problem. Uh, you guys might have seen this before. Why are no the tile itself is covering 3 cells. Like the tile is a domino, right? So this will always cover exactly 3 cells. Okay. So yeah, this is in mode 2025 P2. So the problem is that you are given all of the numbers from 1 to n. And the operation is that you can take any two numbers, a and b, and you can replace these two with a single integer a plus b by 2. And you have the condition that a plus b by 2 has to be an integer. So can you prove that no matter what n is, for all n, you can also, if you know the solution, then like you can try. Just DM me, I'll give you a different problem to try.
Can you please repeat the question?
Yeah, the question is the numbers. You have the numbers 1, 2, comma, and so on till n written on the board. And you can perform the operation on them such that if you take a and b, two different integers that are on the board, you can take them and replace them with their average, such that like the average is an integer. So you want to prove that you can reduce the number of integers on the board to 1 for all n greater than 6. Like for example, take, I mean, just for example, take 5. So, wait, I think there is, oh, just give me a second. Yeah, sorry. Yeah. The operation is that you take A and B and you replace them with A plus B by 2, and like you have A is not equal to B as well. So for example, for this, what you can do is you can take, I think, some, yeah, like you can perform some operation, like you can replace this with, you can take 2 comma 4 and you can replace them with 3. Then on this, you can perform the operation, take 1 comma 3 and replace them with 2. So you will have 2, 3, 5, and then you will take 3 and 5 and replace them with 4. And then finally, you will replace this with 3. Yeah, A plus B by 2 has to be integer.
But isn't n greater than 6?
No, no, just an example, like just to demonstrate how the operation works. Yeah, sure, you can use your mic. Feel free to talk, guys. There is no one stopping you.
I have to prove it for n greater than 6.
Yeah. So, I mean, this is not exactly an easy problem, or like it might take time. So, like, if you have any ideas, just send them in the chat.
The six numbers randomly chosen.
No, they're like the first n integers.
Oh, yes. So we will have two even numbers in the
Yeah.
six, right? We can
Yeah.
add them, and when you divide, we'll get the odd number. Once.
Uh, yeah, but like you want to reduce the number of integers to 1, right? Like you want to be able to perform this operation n minus 1 times. Okay, so I'll give the idea. Like not exactly the idea, but I'll give you a hint. So first of all, we want to prove that the final integer remaining on the board is going to be n minus 2. Okay, try thinking in this direction and now apply induction.
What did you say?
Oh yeah, we want the final number on the board to be n minus 2. Like just you can assume this to be true.
Don't get it.
Like for example, 1, 2, 3, 4, 5. At the end, the last integer on the board is going to be 3, right?
Yeah.
So like you have basically reduced this to a single integer that is 3 and like that is 5 minus 2.
Okay.
So you just want to like the point is that after you have this number 1 2 like you have all of these numbers. So like after performing all the operations, you just want to prove that you end up with n minus 2. And you can take it for a given that like, I'll just give you that there exists operations that send uh, this to n minus 2 and the same for 9.
And how did you think of this kind of idea?
I know this you just get by like I mean this is just basic um, you just like perform operations. There is no exactly motivation for this. You just like play around with stuff and get this. But yeah, the main idea is not this. The main idea is like how will you proceed with this? So, wait, hang on. I think I messed up. I meant n minus 3. Yeah, n minus 3. My bad. Okay, here's a hint. First of all, like assume that you have like you don't know this yet, but assume you prove that for every single odd integer n, like 1 comma blah 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 till 2n plus 1, you can leave 2n plus 1 minus 3. So would this help you prove for all even integers?
Why minus 3?
Not n minus 3, like not for all, but like, if you could prove that it's n minus 3, then it would be helpful, right? Like if you prove that it will reach some point, like if you know that it will reach some integer, then like it's obvious that there will be only one integer, right?
Yeah.
So what do you guys think we should end up now? Just at 2n plus 2. Yeah, perfect. So yeah, if you have it, if you have this statement proved, and then like you have the numbers 1, 2, blah, 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 2n plus 2. So then you can reduce this configuration to 2n plus 1 minus 3 and 2n plus 2. And this will give you that, like this is basically 2n minus 2 and 2n plus 2. So you can reduce this to 2n. So yeah, what we have proved is that if it's true for odd numbers, then for even numbers also it will be true. Now we just need to prove this statement. You just need to prove this. And you are given that like this you are given this information, so what do you think we should end up?
Why is that n minus 3?
No, the n-3 thing is for like odds, not for even. Like you want to prove the n-3 thing for odds is true.
For 1 to 2 and
Sorry?
can we prove?
Not 1 to 2n, but you want to prove like 2n plus 1. Like for example, if it's true for uh, you want to prove that if it's true for like 1 to let's say some like 7, you want to prove that then it will hold for some larger 2n plus 1.
Yeah.
Okay, so first of all, notice that uh, you have this hypothesis, right? You want to prove that this will eventually reduce to 2n minus 2, right? Do you guys get this part? Like this is what you want to prove.
Yeah.
Okay. So now, first of all, for induction, you need to consider like the correct hypothesis, right? For example, consider the hypothesis to this would imply it is true for this. Now, like this you cannot do exactly because this would reduce to like you consider these numbers. Sorry, you consider these. This would reduce to uh, 2n minus 2, 2n plus 2, and 2n plus 3. And now when you take the average of these two, that's the only possible move. It will reduce to 2n and 2n plus 3, and you cannot proceed with this. So like you cannot exactly take this as the inductive step. But notice that the information given is like it's true for 7 and for 9. So what idea does this give you?
2n plus 5.
Yeah, exactly. So you want to prove that if it holds for 2n plus 1, then it will hold for 2n plus 5. And yeah, after this, it's just like construction. So this will reduce to and this reduces to you take these and you take the average, and then you take these two. So you get and then you like and finally you get 2n plus 2. So you have proved that if it's true for 2n plus 1, this would lead to 2n minus 2, right? You also proved that this would imply so does everyone see why this finishes?
Where did 2n plus 3 come from?
Sorry?
Where did 2 and plus 3 come from?
Your voice is a bit unclear. I think it's. Could you
Where
type it?
did 2 and okay.
2n plus 3 in the like no you like you have all the integers from 1 to 2n plus 5, right? So basically if you have 1 comma blah 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 till 2n
Yeah,
plus 5, basically like the whole sequence, and then there are four extra integers.
yeah.
Yeah. Okay, is everyone clear? So basically this was like a slightly harder problem. uh you have to like basically notice that it's not always like it will just be n and n plus 1. Sometimes you need to take like multiple base cases. Like for example, here the base cases were 7 and 9, and you proved for n plus 4 instead of n plus 1. So does
By the
everyone?
way, like, is there non-case bash to disprove 6?
I don't think so. I mean, the case batch for 6 is like very small, so it doesn't matter. So yeah, is everyone clear?
Where did we use indexing? In which step?
We used induction in this step to prove that from 2n plus 1, you can get to 2n plus 5.
I have an alternate solution. Could you please verify?
Oh yeah, sure.
So we separate the numbers from 1 to n plus 1 into two groups. The first group is 1 to n minus 2. And after some time, you can get n minus 4 out of the first group, assuming that from 1 to n, if you after some steps you get n minus 2 from 1, if you consider the group as 1 to n, 1 to n, assuming that you get n minus 4 in the group of 1 to n minus 2.
Yeah, so you're saying like you have n plus 1, so you will first get split this into groups. And
So you can get n minus 4 out of the first group,
yeah,
and then n minus 1. Yeah. So if you average n minus 1 and n plus 1, you get 10.
yeah, yeah, and sure, that would work. Yeah. But I mean, I'm not sure if this works because you need to prove the base case as well, right? The base case is quite important here. Like, for example, if you can't get 8 gives 6, for example, like, then you basically can't use this, right? Because it needs to be true for n minus 1 to be true for n.
Yes.
So, like, yeah, I mean, that could work, but you just need to find the construction for the base case.
Okay.
Yeah, I'll mark the induction step. So, like, this is the hypothesis that we have. Like, if it's true for 2n plus 1, then it would be true for 2n plus 5. And then these are the calculations. Like, these are just the calculations we did to show that it's true.
Why did the question have n greater than 6?
But no, the question didn't have like the question basically was asking like uh, find all n for which you can reduce it to one integer. But like the answer is basically for all n, like only 2, 3, 4, and 6 don't work.
Oh, okay.
Yeah, and 2n plus 5 we consider because like we basically what our idea was, we had like a few steps. So first you prove that, first you have this idea that it could be n minus 3 works for odd. Okay, and you get this kind of idea, like you want to prove that there is some constant integer which will hold for every single n. So now if you have that this n minus 3 works for odd, then this would imply that odd solves even. Odd solves even because, yeah, if you have proved it for odds, then you will prove it for evens. So that is our second step. And then the third step is proving for odds. And notice that there could be a fake solve here if you used even to prove for odd. Like if you prove that 2n implies 2n plus 1, that would be a fake solve, right? Because you're using the odds to prove the evens. So you can't exactly use this step. So you want to prove for, so this will give us the motivation to think of 2n plus 1 implies 2n plus 3. But then we tried that and it did not work. So we then shifted to the next, like the smallest number, which would be 2n plus 5. Okay. Did everyone understand this? Like the whole solution?
I think like for okay, this is for the motivation, like because even I couldn't come up with n minus three, so we can like assume that 1 2 1 2 3 dot 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 n goes to some f of n, and like from there we can work, because like the average, if we work it out for f of n plus one and n plus two, we should get f of n plus one. So from that we'll get a bunch of functions that work, and like from that like we can try which one's base case holds.
Exactly. Perfect. That's the idea. So like, yeah, you know that f of n will be something, and then you have these two n plus 1 and n plus 2, and their parity is different. So like they will have like, it will work with one of these, and then you just need to ensure that it will work for n plus 2 as well. Like Anirudh said, I it's just you need to check the base case. Like he said that this would imply n plus, like n minus 2 would imply n plus 1. So yeah, there were many people who came up with this solution as well. Oh yeah, I'm pretty sure this will also work.
How
No,
to
no,
think, how to
sorry.
think this in NMO, because in NMO, like it's not given that it's true for all integers greater than 6.
No, you have to like I mean you need to like just find that out. Like this is kind of an easier version because it is given that you want to reduce it. But like in the InMo problem, you don't know if it's true. Like you just have to find out whether it's true or not.
Yeah, many people case bash till like 15 16. So yeah, we have
Yeah, I was
that
like
case.
one of them. I also case bashed like 14. And then I like
I
found
gave
out.
up after 7.
So yeah, there are like multiple possible solutions. You can, it doesn't have to be like n goes to n plus 1. Okay, so does anyone have any other doubts? Like you guys understand the motivation for the solution, right? Oh, guys, you can speak up or like at least type in the chat.
Hello, Bhaiya. Uh,
Hi.
actually, I could not join class because of network. Could you please recommend some handout or book for this topic?
Oh, yeah, first of all, like the class is being recorded, so like you can see it on YouTube in a few days. And I would recommend Rushel's combinatorics book. It's an exploration of Olympiad combinatorics. So like it's in stock now, I think, so you can buy it.
Yeah, I have it. Thank you.
Yeah, okay, then cool. Yeah, you can read from there. It's like quite helpful. Okay, so I think it's like 8:30, so like we're done with the class. I'll stop recording.